All right, so now we're going to start talking about explosions. We've gone through our other two types of collisions, and now we're on to explosions. So in that little blank space, I'd like you to pause the video right now, write down 1 or 2 words that define what an explosion is. I'll give you some time to do that. All right, hopefully you've got your word there. I'm going to share my word with you in case you were struggling to come up with one. My definition for these is boom and starts at 0. So those are my 2 words. All right, so then what we want to ask ourselves, and I wrote this question out ahead of time, right? What do we know about total momentum before the collision when we're talking about an explosion? And when we're talking about explosion, we're talking about one object that is starting at rest, all right? So if our object is starting at rest, that means our velocities are going to be 0. And so we're going to have whatever our mass is times 0 plus whatever our other mass is times 0. And so if we're doing anything times 0, our answer is going to be 0. So we are going to be starting with no momentum. Okay? Anytime you find out that you are working with an explosion, the left side of your equation gets really easy because it doesn't matter what mass the objects have. They are going to have no velocity, and so they're going to have no momentum. Okay? So that's the big difference for this type of collision, is that the left side is going to equal 0. All right, then we're going to move on to actually reading through our problem and getting that part all figured out. So we've got a pipe bomb that's exploding and breaking into 2 pieces. So that's why we only need 2 pieces on the right side of our equation. If it had broken into more pieces, we could have added to infinity over on the right side. All right, one piece travels east at 150 meters per second and has a mass of 0.5 kilograms. The other piece travels west, so that's telling me that it's going the opposite direction of the one that's going east, right? So opposite directions, which is good. That's something I should know about an explosion from the reading in our expert groups, right? And it has a mass of 0.1 kilograms. We want to know what is the velocity of the piece traveling to the west. All right, so what we got to do is we have to plug in our numbers. We already solved the left side, so I'm just going to put a 0 right there. And 0 is going to equal the mass of our first object. I'm going to just go in order. And so the first object that it talks about is going to be number 1. The second object that it talks about is going to be number 2. So the first object has a mass of 0.5 kilograms and a velocity of 150 meters per second. The second object has a mass of 0.1 kilograms and a velocity that we do not yet know. That is what we are looking for. That's our goal. All right. Then we take the first part and we want to simplify. 0.5 times 150. We're going to end up having 75 kilograms times meters per second plus that 0.1 kilograms times velocity 2. Now, because of this velocity 2, we cannot add these together. They do not both have the same variable at the end, that V2. If there was 75 times V2, then we could add them together, but we cannot add them together because of that V2. All right, so what we're going to have to do is we're going to have to get rid of this 75 and subtract it to the other side. And so that means we've got negative 75 kilograms times meters per second, which is momentum, is equal to 0.1 kilograms times V2. We're going to divide by that 0.1 kilograms. And again, I ran out of room, so I'm going to write my answer off to the right. negative 75 divided by 0.1 is going to give us a big old negative 750. And this is meters per second, and it is V2. And that's going to be our final answer. Okay. So first, we want to ask ourselves, that's a really huge number. Does that make sense to us, okay? And in order to do that, we're going to have to calculate our change in velocity. And so we're going to do the same order of objects. So change in velocity 1 is going to be our first object. Velocity final minus velocity initial. Our first object had that 150 meters per second. At the end, and they both started at 0 because this is an explosion. And so we have 150 minus 0 ends up being 150. The other one, piece we just calculated for, right, ended with negative 750 meters per second and started with 0, just like the first object. And so that ends up giving us negative 750 meters per second. Okay. And so we ask ourselves which object was bigger. And in this case, object 1 has more mass. Right? Object 1 is 0.5, object 2 is 0.1. So object 1 has more mass. And so it makes sense that it is a much smaller change in velocity. Again, we can kind of ignore the negative sign on the 750. We're just looking at how big the change in velocity is, not really worried about the positives and negatives. All right, that was your example problem. Now we're going to go ahead and we're going to set up problem 2, and you guys are going to finish solving it. Okay. So problem 2 is talking about a man standing in a canoe near a dock. Initially, they are at rest. Okay. Anytime something is at rest, how much total momentum does it have? So that first question asks, P total equals what? And we can say, well, mass times velocity, right? And anytime we are at rest and velocity is 0, our total momentum is 0. Anytime that we are at rest, our total velocity or our total momentum is 0 because our velocity is 0. All right. So now our man tries to step from the canoe to the dock. He moves towards the dock at 1.2 meters per second, and he has a mass of 54 kilograms, and the canoe has a mass of 21 kilograms. Okay. So this problem might not look like an explosion. It's not talking about a bomb. It's not talking about a firearm. It's not talking about anything we typically think of as an explosion. However, because of that, initially they are at rest, and then two pieces go in opposite directions. That is an explosion. So an explosion does not have to be, in quotes, explosive. All right. So then our next question is asking us, what is the total momentum after the man steps towards the dock, and how do we know? All right, this is asking us to talk about conservation of momentum. Conservation of momentum. And that's what we've been using to solve all of these calculations for all of our different types of collisions, right? Conservation of momentum tells us that the momentum before the collision equals the momentum after the collision. And that's just how it works. And so that means that if before the collision our momentum was 0, then after the collision our momentum is also 0. So before, we'll go up in 0. All right. Now we want to know how fast the canoe moves and in what direction. So we're finding out its velocity. Okay. So we're going to use our same old generic equation. Right? The only thing that is special about explosions is that the left side's already done for us and it's 0. That's what makes them special. But otherwise, it's the same old regular equation. and we're going to plug in our pieces. So I'm going to choose that the man is object 1 and the canoe is object 2. And so object 1's mass is 54 kilograms. Object 2's mass, or times its velocity, and it says the man moves at 1.2 meters per second. Then object 2's mass is that canoe, and that canoe is going to have 21 kilograms. And we want to know its velocity, so v2. That's what we're looking for. And that all equals 0. Okay. Then we're going to go ahead and solve, and I'm going to give you guys a little bit of time to do that. All right, so I'm going to go through this and then we'll check our answers at the end. Since the left side of the problem is already completed for me, I'm going to jump right into the right side and I'm going to say 54 times 1.2 because that's my first piece. And that is going to give me 64.8. And my units are kilograms times meters over seconds. Plus, I'm going to keep my 21 kilograms times V2. Now, I cannot add my 21 and my 64.8 because of that V2, because both terms would need to have a V2 attached to them in order for me to add them together. So since they do not both have that letter hanging out, I cannot add them. And so I'm going to have to subtract my 64.8 to the other side. And so that gives me negative 64.8 kilograms times meters over seconds equals, I'm bringing this 21 V2 down, so I'll have 21 kilograms times V2. Now I'm going to go ahead and divide by my 21 kilograms. And that's going to give me negative 3.08, which is V2. And my units are meters over seconds. And that is my answer. So it was asking me though, and I want to make sure I fully answer the question, right? It asked for how fast, and how fast is 3.08, and then it also says what direction, and I have that right here with the negative, right? So if my man, he had a positive direction, my canoe has a negative direction. And so I've answered both parts of my question. All right, so that was how to do explosion calculations. The big difference here, remember, is that the left side is 0. It's always done for us. All right, then I would like you guys to flip to page 17 and 18. Pages 17 and 18 are your homework. There are 4 example problems. Notice that you are going to have to figure out what type of collision is happening before you can solve or pick an equation and solve, okay? There is one thing that I noticed is a little bit confusing. Question 2 talks about a superhero and an asteroid. And instead of giving you masses for both the superhero and the asteroid, it just tells you the asteroid is thrown 1,000 times, or that is thrown, is 1,000 times more massive than the superhero. And so basically what this is meaning is that if the superhero, right, if he has a mass of 54 kilograms, then the asteroid has a mass of 54,000 kilograms, okay? So you could really pick whatever number you wanted and then just add 3 zeros. I recommend that instead of picking a very difficult number, you say, hey, he's 1 kilogram, because that makes math really easy when you have a 1 in the problem. And the asteroid, that's 1,000 kilograms. And I just recommend that because it's easier on the math. You could pick any number you wanted, so long as you make sure you add 3 zeros for the asteroid, you should get the same answer. All right. Then I will let you guys loose. You are finished or working through problems 1 through 4. We're going to check them on Monday. I'll stamp you guys off for having them done, and then we will go through them. Also, if you finish this ahead of time and you have some extra time, remember our 1-pagers are also due on Monday. Have a wonderful weekend.